Hi, welcome to video podcast number 5. Going to be looking at the resolution and collecting power of telescopes in this. Collecting power is pretty quick and easy. Resolution needs a little bit of thinking about. So the background of this is that a telescope works with light as a wave, and that the light from the star can be imagined to be arriving. It's a neat set of wavefronts, actually. Probably it's so distant they should be drawn as straight lines, and that the aperture of the telescope is like the waves passing through a hole, and as you know, waves passing through an aperture will diffract, and that diffraction means that a star, which is essentially a point of light, will not appear as a point of light either on our retina or on an image, and that limits how fine a detail we can see, or perhaps easiest to imagine it, what the smallest angle we can have between two stars and see them as separate. So if we go back to what you should know already, if light passes through a single slit, so here's our ray of light arriving on a single slit, what we would see on the screen if this is coherent laser light is we would see a large central maxima with some smaller side fringes on either side, and that we need to be able to imagine that represented as a graph of intensity against angle. You'll see why this is an important moment. So we've got this very large central maxima, most of the light is in the central maxima, and then we've just got these small side fringes on either side. So it's intensity this way and angle in this direction. And we should know that as we're dealing with small angles, we can say that sine theta is approximately equal to theta. This is in contrast if you've met it to electron diffraction, where the angles are large and we have to use sine theta. And that the angle of this first minima is approximately, because of the small angle approximation, equal to lambda over d. So lambda is the wavelength of the light that is passed through the aperture or slit, and d is the diameter of the aperture or slit. So now we can have a go at applying that to a telescope. And the only real difference in the diagram here is we're going to have to imagine that there are two objects that we're looking at, and we start off by drawing that graph for one star. So we've got our broad central maxima and we've got our side fringes. And if we look at another star, if we can maybe stretch things out a bit just to kind of show what I mean. We're looking at two very widely separated stars, then what we'd see here is simply another star over here, and that's two completely separate objects on our retina or on the CCD of our camera, and that's very clearly two different things. And this is called the Rayleigh criteria for resolution, because the question Lord Rayleigh asked was, as these things get closer and closer and closer, is the point where your eye can no longer differentiate them? And the idea that he had was, he said, let's imagine the closest another star could be is if the maxima of one star was exactly lined up with the first minima of a neighbouring star. And I haven't drawn that completely brilliantly, but you get the idea. So remember, the first minima of that star is separated, so it's the first minima of this star is lambda over d at an angle lambda over d from its maxima. The same with this one, it's lambda over d from that maxima to its first minima. So he said the minimum angle, the maximum angle we can have between two stars, the minimum angle we can have between two stars and still resolve them into two is lambda over d, and obviously that's working in radians. And if you remember back to the little podcast I did on magnification, it's essential that when we're using this equation, we remember that it is a radians equation. And quite often in the same question, I'll just say it again, we might have to think of a distant object and imagine that this distance, we're given the separation of 2 points on the moon or 2 stars. But generally these angles are thousandths, if not millionths of a degree. And therefore it is not, we mustn't treat this as a triangle, we must treat it as a radius and an arc length and do theta equals L over R when we're working with this. We're going to talk briefly now about collecting power. Collecting power is a much simpler idea. And our waves arriving from outer space, and you'll know that astronomers have spent a lot of money building absolutely enormous telescopes. I think the Keck telescope has has a collection of mirrors making up a single mirror, which is about 10 meters in diameter. Now, obviously that's partly about improving the resolution. If we go back here, the bigger D, the smaller theta, and the better the resolution we have between our two objects. Also worth remembering, of course, the smaller lambda is, the better the resolution for the same size dish. So typically a visible light telescope has much better resolution than a radio telescope, simply because lambda is smaller. So small angle is better because it means the two objects can be close and still be resolved. So the Keck telescope, actually, it's not about the resolution, it's simply about collecting more light. We've got to imagine this huge circle, and in some ways it's easy to say it's photons. That's just a huge photon bucket. It's picking up as much light as we possibly can. And if we compare that to earlier telescopes, the Mount Wilson refractor, I believe, was around 5 meters in diameter, so approximately half the linear dimension. But of course what we're interested in is the ratio of the areas, and the area is pi r squared. Of course you knew that. So this area is 4 times more than that area, so it's got 4 times the collecting power because it collects 4 times the photons. Hope you found that useful. Thank you very much.